Good day, students. In this video, we're going to go over force diagrams. Two things that are included in force diagrams are the forces themselves, and we also need to label the direction of the acceleration if there is one. That's an element I left out on Friday, so you'll have to go back and label the accelerations. It's pretty important, and it'll help you solve problems, so please heed my advice there. So here we go. This is the one I showed you on Friday. An egg is falling from a tree. The only force acting on this egg is the force of gravity. And the acceleration is always going to be in the direction of the net force. So acceleration essentially points in the direction of the largest force, which in this case, there's only one force, so that would be Fg. But what I want you to include is the acceleration as well. In this case, our acceleration is exactly 9.8 because there's no air resistance. Basically, gravity is the only force. When something is free falling, gravity is the only force, and therefore A is negative 9.8. But I just want you to label the direction. This is the only force in this problem. The other forces that are possible on this worksheet are normal force, which occurs when something is on a surface, kinetic friction force, which occurs when something is sliding on a surface, applied force, which is a direct push or pull, which, no one's pushing this egg, static friction, which occurs when something is at rest, but there is someone trying to push it or some force that's trying to move it. So this is like when it's trying to move, but it won't. Air resistance is when it's moving through air quickly, or it's moving through air and it's very lightweight. And tension, which is a rope, when something's pulling on it with a rope. So let's keep moving forward. A flying squirrel is gliding from the tree to the ground at a constant velocity. Consider air resistance. So it's not very clearly written, but what I was going for is the squirrel is moving straight down. If you have something different, it might be somewhat correct. Anyway, let's just draw the forces. So best thing to do is go through your list here. There's no normal force, there's no friction because it's not on a surface. There's no applied force because no one's pushing the squirrel. There's no tension because the squirrel is not on a rope. The only two are Fg and F air. Technically, you could draw it in an angle because I didn't really say what direction the squirrel is going. But the important thing to remember about air resistance is that it's in the opposite direction of the squirrel's motion. So I'm saying that the squirrel is moving down. If you think that the squirrel would instead be moving this way, your air resistance would be at an angle or sideways. Basically, if the squirrel is moving to the right, air resistance is left. I'm assuming the squirrel is moving down, so air resistance is up. Let's see what else. We need to draw our acceleration, but have a look at this. Constant velocity. Acceleration is the rate at which velocity changes, so if velocity is not changing, acceleration is 0. Now that we know the acceleration is 0, we know that these two values are equal. F air and Fg are equal because there's no acceleration. It's constant velocity. And there's no other forces on this one. Number 3, a rightward force is applied to a book in order to move it across the desk with a rightward acceleration. Now you notice I'm just drawing squares. You could draw really fancy pictures if you wish. I like to keep it clean. A rightward force is applied. That just basically means someone's pushing it to the right. Someone's taking their hand and pushing it this way, or pulling it. There's a rightward acceleration. So even before I finish my forces, I know that it's going to accelerate that way. So label your acceleration with an arrow. I also have to go through my list. What other forces are here? Is there gravity? Of course there is. It's on Earth. Is there normal force? Of course there is. It's on a surface. What about kinetic friction? Let's label these and give it some thought. Fg and Fn. Friction exists when something is sliding, and of course this book is sliding across the desk, but why is it accelerating? It's because the friction is smaller than Fa. So I'm going to draw a small arrow. I won't be grading you on arrow size. If you have Fk to the left, you're good. But I think it's pretty important to note that. I know that Fa is larger than Fk because it's accelerating this way. We have a rightward net force, which causes our rightward acceleration. Basically, if you're accelerating to the right-facing forces are overpowering this one. And that's all the forces on it. Go ahead and correct those and include a acceleration. Okay. Number 4, a rightward force is applied to a book in order to move it across the desk at a constant velocity. If you compare this to number 3, it's almost exactly the same, except it says constant velocity. So we'll have the same exact forces. We have the same exact forces, however, there is no acceleration. So when there is no acceleration, you just write A equals 0. What this means is that we have no net force, therefore these forces balance and these forces balance. Fg is equal to Fn and Fa is equal to Fk. Therefore we have no acceleration. If your acceleration is 0, your net force is 0. If your acceleration is positive and to the right, your net force is positive and to the right. All right, halfway there. Number 5, a skydiver is descending with a constant velocity. Consider air resistance. Skydiver is descending. Okay. Why is he descending? Well, because of gravity, of course. This phrase, consider air resistance, basically means there is air resistance. Usually we ignore it. Unless it tells us otherwise. Like with a skydiver is pretty heavy, pretty dense, so you might say that we would ignore air resistance. But a skydiver moves very quickly, so that's why we're going to consider it here. But usually I'll tell you to consider air resistance or not. There are some obvious cases, like a feather falling down, where you definitely need to have air resistance because it's so light. It's affected by air resistance a lot. What about our acceleration? Well, constant velocity means acceleration is 0. We can prove this further with some math. This is our old equation for acceleration. Let's say we have a constant velocity of 20. That means that our final velocity is 20 and our initial velocity is 20. Doesn't matter what our time is, because look at this. It'll be 0 over t, which is 0. So there's your mathematical proof if you're more of a numerical person, if you're a numbers guy or gal. Number 6, a force is applied to the right to drag a sled across loosely packed snow with a rightward acceleration. Let's take the two obvious forces. This thing is on Earth, so Fg pulls down. It's also on the surface of the ground, so Fn points up. It's being dragged to the right. Now, this is open to interpretation. You could say Fa, because it's someone pulling it. You could also say Ft, because they're probably pulling it with a rope. But Fa and Ft act pretty much the same, so either one works. And friction will be to the left. Snow has a pretty low amount of friction, but unless I say it is frictionless, there is friction. So, yep, let's look at our acceleration. It's a rightward acceleration. Since we're accelerating right, that must mean that the applied force is larger than Fk. So this sled is going to speed up. That's the meaning of acceleration in this case. This is a trick question for sure. Football is moving upwards towards its peak after having been kicked by the punter. I'm going to actually draw this one. So here's the trajectory. It's going like this. And, ooh, I can't even draw a football. I drew it too small. There's my football. Is there gravity? Yep. Fg points down. Is there normal force? No, because it's not on a surface. Ooh, oh no, we're good. There's no friction because it's not sliding. And one thing that people might put is that there's an applied force. A kick is definitely an applied force, but at this point in the motion, there is no force. It's only moving by virtue of its inertia. It's only moving because it has inertia. That's Newton's first law. Things will keep going unless pulled by a force. So this would continue in a straight line if it weren't for gravity, but there's no applied force keeping it moving. The applied force occurred over here. So at the moment it was kicked, there's a lot more forces. There's Fa, there's Fn, I'm just scribbling because you don't need to draw this. There's Fg down. There might be a little friction between the ball and the ground. So there's a lot of forces here at the beginning, but at this point, it is moving upwards. We're looking at it while it is moving upwards, not as it starts to move. We're looking at it while it's in midair. And that's about it. Gravity is the only force. Once again, we have a downward acceleration of negative 9.8 meters per second squared. So just to hit that home, 8 is negative 9.8 meters per second squared when Fg is the only force. That's our new definition for negative 9.8 because we didn't learn about forces when we learned about negative 9.8. So try to remember that. A is only negative 9.8 when Fg is our only force. Back here with the skydiver, since there's air resistance, we can't consider negative 9.8. Last one, a car is coasting to the right and slowing down. Well, Fg is keeping it on the planet. Fn is pushing up on the car. And this is, well, I'm just going to write friction in here. Friction is causing it to slow down, which means that acceleration is left. So the fact that it's coasting means that they're not pressing on the gas. There's no forward force that's pushing it forward. And so that's how I know it's going to slow down. We can basically think of this car as it's skidding. The brakes are locked and it's skidding to the right. Because in reality, wheels are a little more complicated than that. But when something's slowing down and moving to the right, just, yeah, friction's slowing it down. There's friction in the wheels. There's friction in the axle that's slowing down. So it's not really pushing on the ground, but that is ultimately what's slowing it down. So hang on to these pictures. I mean, please resubmit them. That'll be your grade today. Let's resubmit these on Google Classroom. But also, it's wise to hang on to these pictures, because if you get one of these premises on a quiz, you'll know what the picture is right away. If there's a book sliding across a table at a constant velocity, you know that it's this one. Anyway, I'm rambling. If you have any questions, please shoot me an email. I welcome all questions all the time. Have a good one.